For this problem, we are asked to calculate the Thevenin equivalent voltage, VOC, as well as the Thevenin equivalent resistance, RTH. This equals the voltage across the terminals A and B. Here we have a constant current source feeding two separate branches. Thus, we can identify this as a current divider circuit and solve accordingly. We have the current flowing through branch A and B, so let's dive in. Writing out our equation and solving for VOC, we have this equal to our source current, which is going to be 10 milliamps. Now for a current divider, we are going to multiply the total resistance of the opposite branch, which is going to be 8 kilo ohms, and that's going to be divided by the total resistance of the entire circuit, which is going to be 16,000 ohms. Now, plugging in these variables and solving, we are able to conclude that our VOC is equal to 10 milliamps times 0.5, which gives us a voltage of 5 volts across the terminals. Now, let's solve for our Thevenin equivalent resistance. Now, in order to properly evaluate this, we must transform our current source, and this source can be replaced by an open circuit in which no current will flow. This creates two branches between the terminals and then can be solved as a simple parallel circuit. As you can see here, we have our two branches. So let's go ahead and write out our first equation. We have our Thevenin equivalent resistance is equal to our first branch, which is going to be element 1 of 4,000 ohms, plus our second element of 4,000 ohms, plus our third element of 4,000 ohms. Now, this is in parallel with our second branch of 4,000 ohms. Solving for this, we can simply add up our elements in the first branch to 12,000 ohms, and then to properly evaluate our equivalent series resistance for this parallel circuit, we can multiply 12,000 ohms by our second branch of 4,000 ohms, and that value is divided by 12,000 ohms, once again adding 4,000 ohms. This simplified will give us 48 kilo ohms divided by 16 kilo ohms. Finally, we are able to conclude that our Thevenin equivalent resistance is equal to 3 kilo ohms. Now that we have been able to evaluate not only the Thevenin equivalent voltage, but as well as the Thevenin equivalent resistance, we can then create a equivalent Thevenin circuit that which can be placed into any additional circuit for solving and evaluating. So drawing out our circuit, we have our voltage source with a series resistive element between two open terminals. Our series resistance is going to be equal to our RTH, and our equivalent voltage of VTH is going to be equal to our VOC of 5 volts, as well as our RTH, which has been evaluated at 3 kilo ohms. Finally, we have our full circuit. For this problem, we are asked to calculate the Thevenin equivalent resistance between the two terminals, A and B. Now, this problem may seem tricky, but it is important to recognize that all voltage and current sources must be transformed to their Thevenin equivalent. And we can do so by eliminating the voltage drop across this device. This is done simply by removing the device and replacing it with a bare copper wire. We can do this just like that. Now, this leaves us with a parallel circuit to then solve for. So, Writing out our RTH is equal to the parallel resistance of our 20 kilo ohm resistor, our 4 kilo ohm resistor, and our 10 kilo ohm resistor. This can also be expressed as the reciprocal of the summation of the reciprocal of each of the elements. So 20 kilo ohms plus 1 over 4 kilo ohms plus 1 over 10 kilo ohms. Simplifying and solving, we can conclude that our Thevenin equivalent resistance is equal to 2.5 kilo ohms. We can symbolize this circuit by writing out our series resistance in with our Thevenin voltage and plugging in our value right here.